Today is a very exciting day because we're finally going to introduce another type of function. So we learned about linear functions and quadratic functions, and that's really all that you know in terms of functions. So we are going to study exponential functions. So before I introduce exponential functions, I did want to talk about the linear function and the quadratic function and the different representations. So we have table of values, graph, and an equation. Now, I can tell you that the function is linear from the table if the first differences are constant. I can tell you it's quadratic if the second differences are constant. From the graph, if it's in the shape of a line, it's a linear function. If it's in the shape of a parabola, it's a quadratic function. And we can talk about the equation. If it's in slope-intercept form or standard form of ax plus by plus c equals 0, and the degree is 1, we say it's a linear function. Now if it's a degree of 2, we say it's a quadratic function. And the three different forms were the standard form, vertex form, and factor form. Alright, so now we're going to talk about the exact same representations of an but for an exponential function. So how do I know from a table that I have an exponential function? First, let's give ourselves a table here. Let's say, let's pick some easy numbers. Let's say it's going to be 1/4, 1/2, 1, 2, and 4. Okay, so I can tell you that this table does not represent a linear relationship, because if I were to find the first differences, they won't be constant. Okay, so let's find the first differences. So to go from 1/4 to 1/2, it was increased by 1/4. From 1/2 to 1, it increased by 1/2, and then increased by 1, increased by 2. So clearly, the first differences are not constant, which means you do not have a linear relationship. And if you find the second differences, also prove that you don't have a quadratic relationship. But what I really want to show you is that this table represents an exponential relationship, okay? How can I show that? Well, not only do you have to find the first differences, you have to show that there's a common ratio between successive first differences. So for example, to go from a value of 1/4 to 1/2, you multiply it by 2, right? Because you can say 1/2 divided by 1/4, or you can say 1/4 times what is 1/2? Well, 1/4 times 2 is 1/2. How to go from 1/2 to 1? What's the ratio? Well, you multiply it by 2. And then from 1 to 2, you obviously multiply it by 2 again. So guess what? There is a common ratio between successive first differences, which means that this table represents an exponential function or exponential relationship. All right, now before we do graph, I want to do the equation. Okay, so we have y equals b to the power of x. That is the general form for an exponential function. Now, b, there are some restrictions we have to put on b. And if you think about it, it makes sense based on what we did when we're studying expressions with exponents. So we are going to say b can't be 1. Because if you think about it, if b is 1, you have a very boring scenario. It's 1 to the x, which is just 1. So you have a constant function. So we don't want b to be equal to 1. If we want an exponential relationship, you definitely don't want b to be equal to 1. And then what else don't we want b to be? We don't want b to be negative, okay? Because if it was negative, okay, then for lots of different values of x, you'll get undefined values. For example, if b was, let's say, -2 and x was 1/2, you'll have the square root of -2. And you don't want that. So since we want defined values for y, we have to place an additional restriction for B. We are going to say that B is greater than 0. Okay, if it's positive and it's not equal to 1, it's going to be perfect, beautiful. Okay, you're going to have a beautiful exponential relationship. So there are actually two types of exponential relationships. I'm going to draw out the two graphs, the two possible scenarios. All right, so let's do the first one. And let's do the second one. So really your graph can look one of two ways. Now for either of these graphs, they have something in common. They have an, let's just stick with red here. They have a horizontal asymptote. You know, I'll do both colors because they both have it, okay? All right, so let's stick with the red graph for a second. So this one, as you go from left to right, it's shooting up really, really quickly, okay? So this is y equals b to the x, but there's actually a condition on b. b is greater than 1. Okay, we're gonna explore why that makes sense. So for example, I don't know, let's say if b is 2, then you have this this shooting up effect when you go from left to right. Now, what about the green graph? Well, it's y equals b to the x yet again, but now it's approaching 0. Okay, from left to right, you're rapidly approaching 0. And this happens once again when b is between 0 and 1. So there's actually a name for the green graph and there's a name for the red graph. So for the green graph, it's called an exponential decay function. And for the red graph, it's called exponential growth function. So they're both exponential functions. But one is exponential growth and one is exponential decay. All right. So why does it make sense that it's an exponent? Like, why does it make sense that it's going to grow? You have an exponential growth when b is greater than 1. And why does it make sense that it's exponential decay when it's between 0 and 1? Well, we're going to do lots of word problems that explores the idea, but let's just quickly look at it. So let's pick a value for b that's greater than 1. Well, let's say it's 3. Well, if it's 3, if b is 3, which is obviously greater than 1, I know that this is an example of an exponential growth function. And it makes sense that it's going to shoot up as you go from left to right because your variable is where the exponent is. Okay, so if you increase x, you know, it's 3 to the power 4, 3 to the power 5, 3 to the power 6, 3 to the power 10, 3 to the power 100, so forth and so on. So these values for y are growing very, very quickly. So it makes sense that you're going to shoot up as you go from left to right. Now what about if it's a b value, a base, between 0 and 1? I don't know, let's say a quarter. So this one, it makes sense that as you increase the value of x, the y values will approach 0. It'll never be 0, but it'll get really, really close to 0, right? If you think about it, every time you increase x by 1, you're multiplying by a quarter. You have a quarter of what you had before. Imagine you had one giant cookie, okay? And then you divide it by 4. And you divide it by 4, and you divide it by 4, and you divide it by 4. You know, very soon you'll have very, very little left. You'll have crumbs left over. Okay, So that's, but you know, good news is that you'll always have some part of the cookie left, but it's like I said, it's like probably a few crumbs left over. Anyways, so hopefully when you replace the value of b with either a value greater than 1 or a value between 0 and 1, you'll realize it makes sense that this is the corresponding graph. Okay, whether it's an exponential growth function or an exponential decay function. All right. So let's go back to the table of values just before we forget the idea here. So based on the table of values, we can tell it represents an exponential function because there is a common ratio between successive first difference values. Okay, if there's a common ratio between successive first difference values, you know that the table represents an exponential function. So in this lesson, actually, the big idea is just to talk about exponential growth functions and, well, exponential functions in general, actually, and discuss about their properties. So the domain, the range, intercepts, horizontal asymptote, and whether it's increasing or decreasing over its domain. So the domain is actually easy. Domain is all real numbers, right? You can let any value be for the exponent, okay? The exponent could be a big positive number, big negative number. You can let it be 0. There are really no restrictions. You can let it be a rational number, irrational, whatever you want. But remember, that's as long as b is greater than 0, it's greater than 0 but not equal to 1. That's why we put that restriction there. Okay, what about the range? Well, if you look back at the graph, okay, let's quickly take a look. Whether it's exponential growth or exponential decay, the values of y are greater than 0. Okay, never being 0, they're greater than 0. Oh, so far so good. It seems like exponential functions, whether it's growth or decay, they share a lot of properties here. Well, that makes it easy, right? Ooh, what about intercepts? Intercepts. Well, whether you're exponential growth or decay, you can refer to the graph once again, but there are none. Equation of horizontal asymptote. Well, in both cases, it's y equals 0. Wow, it really seems like they have a lot of they have a lot more in common than what they have in differences. So the really one big difference between exponential growth functions and exponential decay functions is the increasing and decreasing. Okay, so is it increasing over the domain or decreasing over its domain? Well, hopefully you can obviously tell even from the name. Okay, for the exponential growth function, as you go from left to right, it's very clear that it's increasing. As you go from left to right, it's always increasing. Whereas for the exponential decay function, as you go from left to right, it's always decreasing. So, increasing for exponential growth functions and decreasing over its domain for exponential decay functions. And that's pretty much it for our introduction of exponential functions. So hopefully you can tell that you have an exponential function from the table. You can tell you have an exponential function from the equation because the variable is now located where the exponent is. That's why it's called an exponential function. And from the graph, I'm hoping you can tell you have an exponential function as well. One of the key properties of its graph is the existence of a horizontal asymptote. Okay, so let's try the homework.